So we're going to find the distance here, and I'm going to do this by just picking some point. We're going to optimize, but I'm going to just pick some point over here, and I'm going to call it xy. All right? And can we find the distance between point A and this random point xy? The answer is yeah, I can. The way we always did this, guys, is I always think of Pythagorean theorem. So I'm picturing making this into a right triangle. All right? You guys agree this distance on the horizontal this time is x plus 2, right? X minus a minus 2. And likewise, because of the signs, even though it's down, I can write this as y plus 1. All right? Or y minus a minus 1 is what I did, okay? Because we're going to square it. Yes? I'm purposely not doing it perpendicular. Because what we're going to do is we're going to move xy down the line and minimize the distance of d. We're going to make d a minimum for this over. We're going to optimize the equation, okay? So, everybody, do we agree that d squared equals x plus 2 quantity squared plus y plus 1 quantity squared? And again, I can't stress enough, guys, I did this, right, under the covers just now. If you're used to the distance formula, I just did that under the covers. And if you're used to the distance formula, guys, instead of d squared, you guys probably remember it this way, right? Where you all right? Well, if you remember it that way, just square both sides for me, because I'm going to really make your life easier. Because if I leave the square root on it, guys, think about it, we're going to end up taking a derivative here. And a derivative of this is going to be a pain. So what I want to do is optimize this distance right here, right? I want it to be a minimum. I don't want the red line I show currently on my graph. I want to optimize it and get this purple line. And that'll be perpendicular. So let me ask you a question. If I minimize the distance, little d, don't I minimize d squared also? If I make little d as small as possible, isn't d squared as small as possible? Does that make sense, everybody? Here's x. Here's 2 over. Y, the distance between them is y. Y is a negative number in the actual graph, right? So negative 2 plus 1 gives me a distance of 1. You're just getting stuck on the graph picture, aren't you? You take the difference. The difference between x, y, that's the point. So x minus minus 2, y minus minus 1. The difference in points is always the distance. Okay.
Oh, yeah. Mr. Anderson, by the way, I put 3.
Okay. We should. All right. Anyway, coming back to what I just said, though, I really need you guys to agree yes or no that you understand what I'm saying about this next step. If I make little d as small as possible, you guys all concur that d squared, little d squared, is going to be as small as possible too. If little d is 2, d squared would be 4. If I had 2.1, it'd be more than 4, right? So I'm going to optimize, instead of d squared, which leaves me a real problem taking the derivative, I'm going to try to optimize capital D, which is the distance squared. If I make this as small as possible, little d will be as small as possible. It makes the derivatives way easier. So we're going to optimize. And I get x plus 2 squared plus y plus 1 squared. Anybody knows the problem with my equation at the moment? More than one variable. Guys, I can't optimize 2 variables. I got x and y. I have to get rid of one this time. But I love doing distance of a point to a line because guess what? Right there is an equation. Y equals that jump. All right? So I'm going to replace y with negative 3x plus 4. All right? And I'm going to do that in my equation. So d equals x plus 2 squared plus negative 3x plus 4 plus 1 squared. And everybody, I go yippee at this point, right? Because now I have the distance squared. I guess I could write this, d squared equals d, right? I have the distance squared, though, at this point, d, equal to x plus 2 quantity squared plus negative 3x plus 5 if you simplify quantity squared, right? And I now can say this. If I have an equation, we develop this equation, and I want to optimize, I want to take the derivative. All right. You are two choices right now. You can either square all this out, take the derivative, don't, or just keep practicing the chain rule like a bunch of machines, because it's much easier to do the chain rule on this problem. All right? But I'm going to do the chain rule and take the derivative. So I have plus 4. I'm going to change this to plus 5. All right? So I'm going to take d prime. The power up here comes down, right? So I get 2 times x plus 2 to the 1 power. The derivative of the inside is just 1 this time. I'll write it so we see it. Plus, again, derivative of the next one, 2 times negative 3x plus 5 times negative 3. And I know that I'm going to maximize or minimize the derivative. All right, I'm going to have to set it equal to 0. I don't need the second derivative. I am going to take it here at the end to prove it's a minimum, okay, by using the second derivative rule. But we're going to set d prime equal to 0 here. All right, so we'll set d prime equal to 0. So I get 0 equals, distributed to, I get 2x plus 4. Negative 6 is these 2 times negative 3 plus 18x, negative 6 times 5, negative 30. So I get 20x minus 26 equals 0. Awesome. X is 26 over 20. How about 13 over 10? And guess what I just found, guys? I found the x-coordinate of the point that makes the distance a minimum. Now, if I want to prove this is a minimum, I have two choices. All right? I either can do the first derivative rule and check the sign on either side, or I can take the derivative of the derivative here, all right? And I'll tell you right now, d double prime is 20, right? And d double prime is 20, that's a positive number. So the first derivative is 0, the second derivative is positive. What do we always have? We have a local min every single time. That said, then, I've just proven that that's the x-coordinate of the point. I said find the distance. I want the point, guys. If I ask for the point, all I'd have to do would be to take 13 over 10, the x value, and plug it into the line. You guys agree? But I don't have to work that hard. I have developed an equation already right here that is the distance squared based on the x value. Why does the derivative give you that? All right, the derivative gives us that because we have developed this equation that I just gave the arrow to, right? And what do we want to do? We want to minimize the distance. So when we get this in one variable and we set the critical point, we find the first derivative equals 0 and find the critical point. Because we
I don't get why
okay, everybody, do you guys see how there would be a local min on the distance? X and Y changes, so there's a minimum here. Is there ever a maximum in this case? No. This red line can get as long as we want, right? Because lines go on forever. You know, I could go way down here. It gets longer and longer as you go away. So that's why this equation only gives us a minimum, right? Because there is no maximum. If there was a maximum, it would just, we'd have to work our way through that. All right. I want to get the distance. I'm going to plug 13 over 10 into my original distance equation right here and get a value. All right. So I'll box all this stuff up to give us some room. This is all the first derivative and second derivative. Again, proving that it is a minimum. Everybody recall the cheat I used was d squared was equal to capital D. So now I'll go back to d squared. All right, if I do the math here, I get 33 tenths squared plus negative 39 tenths plus 50 tenths. That's 11 tenths squared, and that's going to be equivalent to d squared. All right. And this is a lot of, now it's just plug and chug, right? This is just doing out the math. You know, nothing fun here, actually. Oh, it's always fun. I get d squared is equivalent to 1210 over 100. All right, take the square root of both sides. And I don't know. I don't know what 1210 is divisible by, if it reduces or not. It doesn't seem to. So I'm just going to write this as the square root of 1210. So there's d. That is the distance. If we want 3 decimal points, or 4 decimal points, I'm sorry.
You can do 5 on it.
Can you? Yeah, but does 5 give you something that's reducible?
242 over 20. Then you can do 121 over 10.
Oh, 121 over 10. There you go. Thank you. 121. I should have caught that one. You're right. Which gives you this then as a distance. You're right, Sam. Good catch. Good catch. 121. But everybody. Yep. And everybody, that is the distance. And you might say, Mr. Harrison, that's way painful. It's a lot less painful than finding the perpendicular line, finding the point of intersection, and then using the point of intersection to the original point to find the distance. We just optimized an equation we developed to find the shortest distance.